Hello, in this video we are going to review systems of equations, linear independence, and eigenvalues and eigenvectors from a linear algebra course. Now this is for differential equations, but we're going to review these topics so that we can go through and cover systems of differential equations. All right, so let's start off by looking at a general system of equations. So general system of equations is just going to be n equations in n unknowns. It takes a minute here to write all these out, but let's go ahead and do that. So there's our first equation and our second equation. Through our nth equation. Okay, so that's our general form for a system of equations, just n equations, so n this way, that's equation 1, equation 2 through equation n, and we've got n unknowns, so you've got x1 through xn, and then all these a's are just different, potentially different coefficients that you could have on all of the unknowns. Okay, so using the information from the previous set of videos on matrix multiplication, we can go through and we can take this and we can rewrite it as the multiplication between matrices. So let's go ahead and do that. So in this first matrix, which is n by n, we're going to fill it in with the coefficients from up above. And then in this second, this is a vector. You've got an n by 1 vector. We're just going to put our variables, our unknowns. And then the constants that are on the other side of the equal sign here go in this vector, which is also n by 1. Okay, and if you go through and multiply this out, it should get you back up to above, right? So you could take this vector here, multiply it through by the matrix, and if you do, you take x1 times a11, that gives you a11 x1, x2 times a12, that's going to be a1 x2, and then dot dot dot, and then a1n times xn is going to be that guy. And you just do that down the line, and what you'll end up with is you'll end up with an n by 1 vector equal to this n by 1 vector, and when you set those equal on each side, you'll get that, you'll get this equal to b1 and this equal to b2 and so on. Okay, so this is the matrix form. For a system of equations. And so what we can do now is we can go through and actually turn this into a matrix equation by taking this big thing here, this big matrix, and calling that A, taking our vector here, calling that X, and we're going to put a little bar over it to represent the fact that's a vector, and then taking our vector B here and putting a bar over it. And then this is our matrix equation. So the cool thing is we went through and took a system of equations where we have n equations with n unknowns, and we were able to go through and rewrite that as a single equation made up of matrices and vectors. So some information about that. Let's just transcribe that over here. So we've got AX equals B. This is our matrix equation. Okay, so some facts, if B is 0, right, then we would have AX equals 0. If that's the case, then we say that the system is homogeneous. Otherwise, non-homogeneous. Okay, and then also if A is invertible, right? So we went over inverses in a previous video, previous linked video. If A is invertible, which I'll comment on that in a second. If A is invertible, that just means that it has an inverse. If A has an inverse, then you can go through and you can solve this matrix equation by doing something very similar to the way that we would solve a regular equation. Right, so if you think of this as kind of A times X equals B, what we'd like to do is to go through and multiply by the thing that would cancel out A. Well, that would be A inverse. And if you do that on both sides, A inverse times A produces the identity matrix. They kind of cancel each other out in that way. And then anything times the identity matrix is going to be itself. So we're going to get X equals A inverse times B. So if you can go through and you know that A has an inverse, then you could go through and do a process like this, which would enable you to solve the matrix equation using the inverse. Okay, so I've said a couple times that if you know A has an inverse. So the video that I linked that went through and covered that content, I believe it showed you how to calculate that A has an inverse, but it didn't show you a method for figuring out whether A has an inverse. So there is a quick and easy test. So the test to determine whether A is invertible is to go through and calculate the determinant. And so I did link a video on determinants as well. And so if you go through and calculate the determinant, if the determinant of A is not equal to 0, then A is invertible. A has an inverse. So you could go through and just quickly calculate the determinant, and that would tell you whether you could go through and do this. So this, you can only do this if the determinant of A is not 0. Okay, so that's a way to go through and solve a system of equations. Sorry, solve a matrix equation, which represents the system of equations. However, there are ways to go through and solve systems of equations by hand. And so I'm going to go through them quickly because we actually are going to use this technique later in the video. This is by hand, but still using matrices. So there's other ways to go through and solve systems of equations, of course, but we do still want to use matrices. So, and I'm just going to show you with an example. It's the easiest way to do it. So let's say we've got x1 minus 2x2 plus 3x3 equals 7. And we've got negative x1 plus x2 minus 2x3 equals negative 5. And 2x1 minus x2 minus x3 equals 4. Okay, so we've got a system of equations. It's got 3 equations, 3 unknowns. And we want to go through and we want to use matrices to solve this. So the way to go through and solve this using matrices by hand is to create what's called an augmented matrix. So an augmented matrix, you go ahead, and it's a little bit similar to what we did on the previous page, except what we're going to do is we're going to take the coefficients here, and we're not going to put the x's anywhere. We're going to take the coefficients, we're going to put them here on the left side of this dashed line. Like that. So this is called an augmented matrix. And then what we're going to do is we're going to go through and use row operations. So row operations were covered in a previous video. Like for example, you went through and found inverses, and when you found inverses, you used matrix operations. So we're going to go through and use matrix operations, and what our goal is going to be to do that is to go through and convert the left-hand side here of the this augmented matrix, to convert it into row echelon form. So row echelon form has along the diagonal, we have ones or zeros, and below the diagonal, we have zeros. All right, so let's just get to it, and you can just see with an example, right? So we want to start off with the one here on the diagonal, start off with the one at the upper left, and then we're going to go ahead and kind of use that one to get rid of all the numbers that are beneath it. And the way that you do that is you take this row here, and you're going to add multiples of it to the rows that are beneath it. And you're going to do that to get rid of these numbers that are beneath it. So how would you do that? So if this is a 1, we've got a -1 here. The way that you'd get rid of a -1 is by adding 1 to it. So if we take the top row and add it to the second row, that will get rid of that -1. So I'll show you how that works. So 1 plus -1 is 0. So the way that I did that is I took this and I added it to that. I took the first element of the first row and added it to the first element of the second row. So if you do that for the first element, you need to do it for all the rest. So we're going to take -2 and add it to 1, 3 and add it to -2, 7 and add it to -5. Okay, and so you can see we've got a 0 there now instead of the -1. And now we want to go through and get rid of the 2. We're going to do the same thing, except to get rid of a 2, we would need a -2. So we're going to take -2 times the first element here and add it to the second. Add it to the third one here. So if we take -2 times 1, we get -2. -2 plus 2 is going to be 0. And now if you do it to the first guy, you need to do it for all the rest. So we took -2 times the first element and added it to the third. So we need to take -2 times the second here. So -2 times -2 would be +4, and then add that to -1 to get 3. And then we're going to take -2 times 3. That's going to be -6. Add it to -1 to get -7. And take -2 times 7, that's -14, and add it to 10, and we get -10. Okay. And now once we've gone through and done that, you can see we've got a 1 on the diagonal and zeros beneath it. So next we want to go to the second column here, and then we want to get a 1 on the diagonal. So to do that, you're going to take this second row and you're going to multiply it by -1. Got 1, -2, 3, and 7, 0, 1, -1, -2, and then 0, 3, -7, -10. Okay, and then beneath the diagonal, we want to go through and get zeros down there. So we can take this, to do that, we could take the second row here, and we could take, to get rid of a 3, we need a -3. We could take -3 times the second row and add it to the third row. And if you do that, you'll get 1, -2, 3, and 7, 0, 1, -1, -2. And then, so -3 times 0 plus 0 is 0. -3 times 1 is -3 plus 3 is 0. -3 times -1 is 3. 3 plus -7 is -4. 3 times -2 is -6. -6. Oh, hold on, sorry, that was -3. -3 times -1 is +3. That one's right. So -3 times -2 is +6. +6 and -10 is going to be -4. And then the last guy here is on the diagonal. We want to have 1. And so we could do 1, -2, 3, and 7, 0, 1, -1, -2, 0, 0, 1, 1. All right, so once you've done that and you've got ones on the 1 or zeros on the diagonal and you've got zeros beneath the diagonal, this is called row echelon form. And from there, you can go through and easily solve the equation by translating it back. So how did we translate it from system to matrix? Well, we took the coefficients, put them over here. We took the numbers on the other side of the equal sign, put them here. So you just want to do the exact same thing, except in reverse. So we want to take these numbers here on this side and make them coefficients. So we're going to have x1 minus 2x2 plus 3x3 equals 7. And then we're going to have x2 minus x3 equals -2. And then we're going to have x3 equals 1. Okay, coefficients on this side. So you got 1, -2, 3, 1, -1, and then 1. And then diagonal, which is where the dashed line represents the equal sign, and then take these and put it on the other side of the equal sign. And if you've gone through and done that, once you've done that, you can go through and solve the system by what's called backward substitution. So we've got x3 is 1. So now take 1, plug it into the equation above, and you can figure out what x2 is. And then once you've got x2, take that and plug it into the equation above, and you can figure out what x1 is. So let's go through and just quickly do that so we can see how that works. So we've got x1. Let's copy this. So what was it? It was x1, -2x2. It was 3x3. Yep, equals 7. And then we've got x2 minus x3, I believe, and then 4? Nope, -2. Nope, that's why you don't guess. And then x3 equals 1. And so backward substitution, we want to take this and substitute above. So we're going to have x2 minus 1 equals -2. So x2 is going to equal -1. And then once we've got these two, backward substitute again to the guy above. So we've got x1 minus 2. x2 is -1 plus 3. x3 is 1 equals 7. So we've got x1 plus 2 plus 3 equals 7. And we get x1 equals 2. Okay. And so if we go ahead and take all those and put them together, so this is the way that we represent this. So if we've got x, which equals x1, x2, and x3, so this is our solution vector, you could pop them into that and we get 2, -1, 1. All right, that's our solution. Okay, and so that's how to go through and solve a system by hand. Now, the one thing is that we got a nice single solution here. That's not always going to be the case. Sometimes you go through and solve these systems and you get a single solution like this. Other times you get no solution. Other times you get infinite solutions. So the infinite solution case is the one that we're really interested in. So if there's no solution, what's going to happen when you go through this process? If you go through and do this, turn it into a matrix, and then you go through and do the row reduction, what you're going to get is you're going to get an all 0 row on the left-hand side of the dashed line, and then a number other than 0 on the right-hand side of the dashed line. Okay, so if you want to think about like this problem here, if this had happened, if we'd gotten 0, 0, 0, and then a 1, if we translated that back, we would have had 0x3. If you've got 0x3, you get 0x1, 0x2, and 0x3, then that's telling you that the whole left-hand side is 0, and so you'd have 0 equals 1, which is just not true. And so that's what's going to happen if you get a system that doesn't have a solution, is that you'll get something that's impossible. However, another possibility is that you'll have a system that has an all 0 row. So 0 is to the left of the dashed line and 0 to the right. So that what that means is that you have infinite solutions. And we do want to take a look at that case, because that's the case actually that's going to come up later in the video, is that infinite solutions case. So what do we do when that happens? All right, so here's a system that is going to give us infinite solutions, and we can take a look at how to solve it. All right, so let's go through and do the same process we just did a minute ago and see what happens. So first we've got 1, -2, and 3. Put our dashed line, 7, -1, 1, -2, -5, 2, -1, 3, 8. Okay, and so the goal is the same. And a large part of this matrix actually is the same. So let's just go through this quickly. So we've already got the 1, so just leave it. To get rid of this -1, you're going to add. So we've got 1 and -1 is 0, -2 and 1 is -1, 3 and -2 is 1, 7 and -5, 2. And then we're going to get rid of the 2 here, we need a -2. So take -2 times the first row and add it to the second. So we got -2 plus 2, 0. -2 times -2 is 4. 4 and -1 is 3. -2 times 3 is -6. -6 and 3, we get -3. And then -2 times 7, we get -14. -14 and 8 is going to be -6. Okay. And then next we can go through and get the 1 here. So we've got 1, -2, 3, and 7. 0, 1, -1, -2. So to get a 1 here, we're going to negate this row. And then we've got 0, 3, -3, and -6. Okay, and so an observation that you can make is that if you see one row is just a multiple of another row, like exactly a multiple, so you take this row and you multiply it by 3 to get each of these elements, that means if we took -3 times the second row and added to the third, it's going to wipe out that row. So we're going to have an all 0 row. So the all 0 row, that's what tells us we've got infinite solutions. So we're going to have 1, -2, 3, and 7, 0, 1, -1, -2, and 0, 0, 0, 0. Okay, so here's row echelon form, and you could go through and translate this back and then do some back substitution, but there's actually a simple step. You can do one more simple step here that's actually going to be it's going to speed things along, and that is to put this into what's called reduced row echelon form. All right, so if we've got reduced row echelon form, the difference between row echelon form and reduced row echelon form is that reduced row echelon form, you get above the 1s. So if you've got a 0 along the diagonal, then you don't do anything there. But above the 1s, if you can, like here, you're going to go through and get a 0 there as well. So not just as before, what we said is that row echelon form, you've got 1s or 0s along the diagonal and then 0s below. Reduced row echelon form, you've got 1s or 0s along the diagonal, and then above and below the 1s, you have 0s. So it's just going to add one more step here, and that one more step is just going to speed things up. So let's go ahead and do that. So to get rid of the -2 here, you're going to need a +2. So we're going to take +2 times the second row and add it to the first row. So if you do +2 times 0 and add it to 1, you get 1. +2 times 1 and add it to 2, you get 0. +2 times -1, you're going to get -2. -2 and 3 is 1. And then +2 times -2 is going to be -4. -4 and 7 gives us 3. And then the second row stays the same. Third row, 0s. Okay, and now that we've done that, now we can go through and take that and translate it back. So you're going to get x1, okay, and then 0x2 plus x3 equals 3, right? So this dashed line still is where the equals goes. And then for the second row here, we've got x2 minus x3 equals -2. And then what do you do with this all zero row, right? What you're going to do is you're going to use what's called a free variable. We're going to say x3 equals x3. So you're going to take the missing number here that we've got, you're going to set it equal to itself. Okay, so if you've got a 1 missing, the place where you have the 1 missing, you're going to take the variable that's represented there and you're going to set it equal to itself. All right, so what we can do here, let's just translate this over to the next page. So we've got x1 plus x3 equals 3, x2 minus x3 equals, was it 2, I think? -2. Equals -2, and then x3 equals x3. Watch this, we can go through and take this first equation and get x1 by itself by moving the x3 over. And so you're going to have negative x3 plus 3. And then we could take this equation and we can move the x3 over, and we're going to get x2 equals x3 minus 2. And then this equation, we can just take it and rewrite it. And you get x3 equals x3. All right, so take a look at that. We've got x1 defined in terms of x3, x2 defined in terms of x3, and x3 defined in terms of x3. And so we can do this cool thing where we just go through and do x equals. All right, and what we're going to do is we're going to take the coefficients here from this first guy. So this is -1, 1, and 1 times x3. So it's like we factored out the x3. And then over here, we're going to take the numbers that are left, and we're going to have 3 and -2 and 0. Okay, and so this represents the same thing as this. It's just written in vector form. If you wanted to kind of see that x itself, when you write x in vector form, it's x1, x2, x3. So essentially what I just did is took this and turned it into vectors. Okay, so we've got this side, that's a vector, this piece, that's a vector, and this piece, that's a vector. Now, the cool thing with this is that you can go through and so we said that there's infinite solutions, is that we can now generate solutions by plugging in values for x3. So what we can do is we can go through and say, all right, well, if x3 equals 1, then what does that mean? We're going to get x equals 1 times this. That's going to be -1, 1, 1 plus 3, -2, 0 equals -1 and 3 is 2, 1 and -2 is -1, 1 and 0 is 1, and that is going to be a solution to the system. And you could go through and say, well, what about if x3 is 2? Well, again, there's infinite solutions here, so you can go through and generate as many as you'd like. So we're going to have -1, 1, 1 times 2 plus 3, -2, 0. Let's see if we can squeeze this in over here in this corner. All right, so we're going to have 2 times -1, that's -2, -2 and 3 is 1. 2 times 1 is 2, plus -2 is going to be 0. And then 2 times 1 plus 0 is going to be 2. And so this is also going to be a solution, right? So we've got infinite solutions, and we can go through and we can generate them by using our free variable here. Okay, and so this method that we just went through here, this is going to come up again toward the end of the video, so we are going to need that. But first, let's go through and spend a few minutes talking about linear independence and linear dependence. All right, so what does it mean to be linearly independent? So we're going to talk about this is discussed in terms of the context of vectors. So we say a set of vectors is linearly independent if no combination of any n-1 of the vectors can generate the remaining vector. All right, so if we've got n vectors, if you go through and picked out one of those vectors, picked out one of them and pulled it aside, can you take the rest of the vectors and generate that remaining vector with it? If not, then it's linear. Then the vectors are said to be linearly independent. They're linear. The vectors are linearly independent. If you took n-1, if you took one of the vectors out of the group, and then you can represent that vector with the rest of the vectors, then they're said to be linearly dependent. Okay, so we've got independent is when you cannot take n-1. You can take one of the vectors away and represent it with the rest, and dependent when you can. Okay, so that may seem like an esoteric definition. So another way to think about it is, are the vectors uniquely different? So the question is, how different are the vectors in your set of vectors? So let's look at it at some examples to maybe try and illustrate that. So here's a set of vectors. The question is, how different are these vectors? If I took any two of them, can I use two of them to represent the third? If you took combinations of these two, could you get this one? Or if you took combinations of these two, could you get this one? Right? And the last of the three, which one I do is say combinations of these two and get this one. All right, and if you think about that, the answer is no, right? So what are the combinations? So what do we mean by combinations? It means you take multiples of this and multiples of this and add them together, and can you get this one? Right, so can you go through and take a times 1, 0, 0 plus b times 0, 1, 0, and can you go through and get c times 0, 0, 1? And the answer is no. If you go through and just try to solve this, what happens, right? So you're going to get, this is going to be a times 1 is a times 0 is 0, a times 0 is 0, b times 0 is 0, b times 1 is b, and then b times 0 is 0. So if you go through and multiply and add these two together, that's what you get. And if you go through and multiply this one, this is what you get, right? Oops, sorry, there should be a c in there. Right, and so what values for a, b, and c would make this true? And the answer is none. No, there's these things are not equal. There's no, well, hold on, I should qualify that. You could say, well, a and b and c could all be 0. If they are all 0, then these two would be equal. That's a special case that we're going to talk about in a moment, actually. That's a very important observation, is that if a, b, and c were all 0, then these would technically be equal. So what we're looking for is there a set of solutions where all three variables are not 0? And the answer is no. There is nothing. There is no combination of these other than 0 that would make these equal. Okay, and that's by comparison. Let's look at a second example, which I think we can squeeze in onto this page. If I went through and I said that you have vectors 1, 1, vectors 1, 0, and 0, 1, and I said, how different are these vectors? Could you take two of these vectors and generate the third? The answer is absolutely. You could take these two and we could use combinations of these two to get the remaining one. And what would those look like? Well, if you took a times 1, 0 plus b times 0, 1 equals, oops, there should be a c in there, equals c times 1, 1. then all it takes is A equals B equals C equals 1, and these would be equal, right? And so in this case, since there is a way to take two of the vectors and generate the third, this is linearly dependent. So if you can go through and do it, then they are not very different. The vectors are not different enough. So they're dependent on each other. You could think about it that way. They're dependent on each other. Meanwhile, if it's not possible to take two of them and combine them to get the third, then that's when we would say that it's independent. Really not enough room here. Let me erase this none here. So this case, we would say this is linearly independent. All right, and so what linear dependence / independence does is it goes through and it measures how different vectors are. So we've got a set of n vectors. Can we represent one of the vectors with the others? If so, then they're not very different. They're not different enough from each other, and we would say that they're linearly dependent. If not, then we would say that they're uniquely different. You can't go through and use some of them to get the others, and so that's when we would say that they're independent. All right, you can go through and think of this geometrically in terms of distances. That might help. If you were to go through and think about this in terms of directions, sorry, not distances, but directions. If you think about it, the question is, can you take, are you pointing in different directions? And if you look at these vectors, this vector points in the x direction, this is in the y direction, this is in the z direction. Those are completely different. This vector points in the x, this vector points in the y, this vector points between the two. And so you can take x and y and combine them to get this vector. And so we have the directions are not different enough to be independent. So here we've got three different directions that where you cannot take two directions and combine them to get the third. And that's the independent case. And here you've got two directions. You can take two directions and combine them to get this third direction. So that's the dependent case. Okay. So the question is there some way that we could go through and test for whether we have linearly independent vectors or whether we have linearly dependent vectors? Okay, and yes, there's a way to test it, and it comes back to this somewhat, the kind of the more esoteric version of the definition, where we think in terms of is there a way to pull one of the vectors out and use that to generate the rest? Okay, so that's the question: is is x1 x2 dot xn linearly independent? That's the question we want to answer. And what we'd like to do is come up with a test for that. So what would that test look like? Well, so we know that they are going to be linearly independent if you go through and create an equation where you've got C1 times, actually, let's do it this way. We've got Cn xn. So we go ahead and just grab. So these are the order here is arbitrary, but we're just going to take the last one and we say, can we take the last one and represent it as a linear combination of the others? Okay, so if we could do this, if this were possible, then it would be linearly dependent. Okay, that would mean that one of the vectors, so they're not different enough. One of them can be represented with a combination of the rest. So what we want is we want for this to not be possible. All right, so the only issue here, all right, so hold on. So if this is not possible, so we want this to be not possible. That's what we want. All right. Now, the issue is that it's guaranteed to be possible if we go through and just take all of the C subscripts and we just make them 0. So what we mean by not possible is what we want is we want that the only way that this could be true is if C1 equaled C2 equal ... equaled Cn equaled 0. If this is the case, then this doesn't count. That doesn't mean that you could take a combination of them and get the others. That's the case that we discussed here, where if A, B, and C are all 0, well, yeah, then technically this equation is true, but that doesn't mean that you could take 2 of these and get the others. All right, and so that's essentially, that's the situation that we get when all 3 variables are 0. That's the situation that we get when they're independent. And so what we want to have happen is if you ask this question and you go through and grab a 0, grab this equation here to represent 1 as a combination of the rest, then what we want is we want for that to not be possible. And we know that when that's not possible, what happens is that the coefficients are all 0. That just tells you that if you go through and you make all these coefficients 0, sure, you get 0 equals 0. That's technically true, but that doesn't tell you that you could take this guy and represent it as a combination of the rest. Okay. Well, so if when this happens, we want this all to be 0. That's another way of saying that when the following happens, this is equivalent. All right, so this is, if we've got this, then this is equivalent. And so what we want is we would say, all right, well, if when this happens, we would get this. Well, then when this happens, we also want, the only solution is C1 equals C2 equals ... equals Cn equals 0. Okay, well, if this equation here, if when this happens, we want the only solution to be this, well, we could take this and we could actually rewrite this into a matrix. So check this out. All right, so what we could do is we could take x1 here and put that here in the first column. So this is x1. x2 we could put here in the second column, through xn here in, so these are vectors, so they've got n elements, and so we've got we've got n things here and n things here and n things here, and then we could say c1 c2 ... cn equals, so we could take this equation here and we could turn it into a matrix equation. Or I'm sorry, this is an equation. This is I guess it's a matrix equation. But to make it look a little bit more like the matrix equations we've written before, what you can do is you could take these vectors and you can write them out. And if you do that, it will look a little more familiar. Right. So what we're going to do is we're going to say x1 has n elements, so that would be x11, x21, ... through xn1, and then the next one here, that's x2. So that's going to be x12, x22, ... through xn2. And then we'll have the nth guy here. We'll have x1n, x2n, ... through xnn times c1, c2, ... through cn equals 0, 0, ... 0. All right. So if we start off here, you take one guy and you could represent it as the rest, and we want that to not be possible, so this gets the solution. We could take this and this is the equivalent of that. Then we could take this and we could say this is the equivalent of that. And then we could take this and say that this is the equivalent of that. And so all of this is to say that if you go through and you want the vectors to be linearly independent, then when we write this matrix, we want the only solution is C1 equals C2 equals ... equals Cn equals 0. So this will be this. So this is we're gonna have linear. The answer to this question is, are these vectors linearly independent? Given this, if this is the case, then the answer is yes. Given this, if this is the case, then that's the same thing as saying given this, that this is the case. And that's the same thing as saying given this, that that's the case. And that's the same thing as saying given this, that that is the case. And so what we can do is, if someone asks you, is x1 through xn linearly independent, if you go through and create a matrix that's made up of them, as I did here, this is the first vector, second vector through nth vector. If you solve that matrix equation and you get that the solution is C1 through Cn equals 0, then that's going to be linearly independent, right? So if this is true, this is the linearly independent. This is linearly independent. This is another way of saying that you cannot go through and represent x1 through xn as any one of x1 through xn is a combination of the rest. So let's go through and see this test in action, so you can see how you do it, how, what the actual steps are, what that looks like, right? So you're asked to go through. You're asked to is 1 to -1, 2, 1, 3, -4, 1, -11, linearly independent. That's the question. Are these linearly independent? All right, and so what we're going to do, we're going to depend upon what we just went through and did. All right, and so the answer is going to be if when we go through and create a matrix equation like this, if the only solution is this, then it's linearly independent. All right. So how do we do that? Well, take these guys, make this one the first column, make this one second column, make this one the third column. That's what we did right here. Oh, oops. And then what I'm going to do, I'm going to kind of cheat a little bit. I meant to do that right here, but I forgot to. You can take, if this is a system, we can go through and we can translate this into an augmented matrix, like we did all the way back, right? Like we did back here, right? We could make that into an augmented matrix. And so I'm going to go ahead and do that right here. So we can go through and do ... 0, 0, 0. Right. So instead of writing this and then equals zeros, you can take this and you can turn it into an augmented matrix by taking this as the coefficients, then doing a dashed line, and then the stuff on the other side, the equal sign, like we did back here, right? So you took this as the coefficients, dashed line for the equal sign, and then the numbers on the other side. Here we have coefficients, numbers on the other side. And so you can just kind of take this and get rid of it and put a dashed line in place of it. All right. And so if you go through and do your row operations on this, what happens? So we're going to do first, we have the 1 here. So go ahead and leave the first row alone. Then we're doing -2 times the first row and adding it to the second. -2 times 1 plus 2 is 0. -2 times 2 is -4. -4 and 1 is -3. -2 times -4 is -8. Or sorry, +8. +8 and 1 is 9. And then -2 times 0 plus 0 is 0. Okay, hold on. Let me check that one more time. So -2 times 1 plus 2 is 0. -2 times 2 is -4 plus 1 is -3. And -2 times -4 is +8 plus 1 is 9. Okay, that is correct. All right, and then to get rid of the -1 here, we could just take the first row and add it to the third row. So we're going to do 0, and then 5, and then -15, and then 0. All right. And now if we go ahead and look at the third row and compare it to the fourth row, we could see that the elements from the, we've got, there's a 3-to-1 ratio between this guy and this guy, the 3-to-1 ratio between these two, and they're off by a negative there. So anyway, this second row and the third row are in the same ratio. And so we can go through and without even doing any calculations, you can know that you're going to be able to cancel. You're going to be able to get rid of one of those. So let's get rid of the third one there. So we're going to have 1, 2, -4, 0, 0, -3. Well, actually, let's go ahead and while we're at it, let's let's divide this row by -3. And so we're going to have 1, -3, 0, 0, 0, 0, 0. And then finally, to put it into reduced row echelon form, we're going to take -2 times the second row and add it to the first row. If we take -2 times 0 and add it to 1, we get 1. -2 times 1 and add it to 2, we get 0. -2 times -3 gives us 6. 6 and -4 is going to be 2. And then -2 times 0 added to 0, you get 0. Okay. And so what have we got here? This system here. So we're using C's, right? So these are C's, not X's. Don't get confused here. So we're going to use C. So we're going to have C1 plus 2C3 equals 0. And then C2 minus 3C3 equals 0. And then for the missing row, we've got C3 equals C3. And so this is another way of saying we've got C1, C2, C3, which equals our C vector. And that's going to equal, oh, whoops, I forgot a step here. I skipped a step. You need to get the C1 by itself. So you have C1 equals -2C3. And you're going to have C2 equals 3C3. And C3 equals C3. And so we're going to get -2, 3, and 1. C3 plus plus 0, right? There's nothing else there. Okay. Plus 0. So this is saying that C1 C, our vector, equals -2 times 3, -2 times C3 for the first component, 3 times C3 for the second, 1 times C3 for the third. And we have infinite solutions, right? Anytime you get an all 0 row like that, we've got infinite solutions. So what was our circumstance under which we got linear independence? We said that if we have this, and the only solution is this, where we get all zeros, then it's linearly independent. So was the only solution that C1, C2, and C3 had to all be 0? No, we got a solution here where if you take C3 and you plug in 1, then we say C1 could be -2, C2 could be 3, and C3 could be 1, and that would make this equation true. And so because of the fact that there is a solution other than all 0, this is going to be linearly dependent. So is this linearly independent? The answer is no, not linearly independent. All right, so because of the fact that we were able to go through and get a solution other than all zeros, what would have happened here for it to be linearly independent? Okay, so how would we have known if this was linearly independent? Right. Well, what would have happened is we would have gone through and we would have had 1s all the way down the diagonal. You can't have an all 0 row. If you have an all 0 row, then it's linearly dependent. If you have 1s all the way down the diagonal, then it's linearly independent. And it's that simple with these. All right. So all 0 row, dependent. No all 0 row, independent. Okay, so that's the way that you can go through and do this test. Is once you've got the vectors, take the vectors, use the vectors to form your matrix, augment it with zeros, solve. If you get 1s all the way down the diagonal, you're good and it's independent. If you do get an all 0 row, like we did in this problem, then it's going to be linearly dependent. Okay. Is there a shortcut or is there a faster way to do this? Yes, there is. So let's go back to the question where we said if we have x11 through x, how did I do it? I don't remember already. You know what? There's enough room on this page. Let's just, rather than me rewrite the whole thing, let's just jump back to that page. All right, so you're here. All right, so if we take this and we translate it into our our matrix equation. This is another way of saying that x, to represent this, times c equals 0. Okay, if you took this matrix and represented it as x, you took this vector and represented it as c, and you took the zeros here and you represent that as 0. And then the question is, when what circumstance under which would we be guaranteed to have the only solution is c equals 0? So when would c equals 0 have to be true? Well, if x were invertible, then you could do x inverse times c equals x inverse. And if you did that, x inverse times x would be I times c, and x inverse times 0, anything times a 0 vector is going to be 0. You get c equals 0. Okay, and so if the vector we create here, if that's invertible, if that has an inverse, then that means that we're guaranteed to have c equals 0 be the only solution. Okay, and so instead of going through and creating this this augmented matrix with zeros and doing all these steps, what we could do instead is ask ourselves, is x, no line over it, is x, is the matrix that we would create from the vectors, is x invertible? So that gives us an alternate way to go through and do this. And the question is, which is faster? Is it faster to go through and augment with zeros and then see if by solving it, we get that the only solution is that C1 through C3 are 0? Or is it faster to go through and take the matrix here and determine, is it invertible? All right, well, earlier we said that we have a test for invertibility, right? What was that test again? The determinant. If the determinant of A is not equal to 0, then that gives us a quick test for whether we have whether the matrix is invertible. And so what we could do is, instead of doing all of this step, we could just take the matrix here. This is x, and we could go through and just calculate the determinant. So the determinant of x would equal the determinant of what did we have? So we have 1, 2, -1, and then we have 2, 1, 3, and then we have -4, 1, -11. And so our determinant calculation, we take 1, multiply it by the determinant of this 2 by 2, so that's going to be -11 minus 3, that's -14, minus 2. This guy times the determinant of this 2 by 2, so we're going to get -22 plus 1, that's going to be -21, and then -4 times 6 plus 1. All right, so we've got 6 plus 1, that's 7. So that's -14 plus 42 minus 28. -14 plus 42, that's good, that is 0. So the determinant of A does equal 0, which tells us, what does that tell us about x? So x is not invertible. If x is not invertible, then this is not independent. Okay, so that's what we're talking about here, is that if we go through and take this and rewrite it as a matrix equation, what we want to know is, when would we be guaranteed that c equals 0? That's going to be where we get independence. We would be guaranteed to get independence if x is invertible. If x is not invertible, then we get dependence. And so in this case, the fact that we got 0 is what tells us that it is. It tells us that x is not invertible, and thus the vectors are linearly dependent. Okay, so what would we have needed to get here for them to be independent? So one quick comment here. This verifies what we got on the previous page, right? So the previous page, we got that they were dependent. So the fact that we got 0 verifies that they are dependent. What would we have needed for them to be independent? We would have needed to get something other than 0. If this were not 0, then they would be independent. And that would align with the case where we do not have an all 0 row. So if you take the vectors here, form them into an augmented matrix like this, they will be independent if there's no all 0 row. They will be dependent if there is. If you take the vectors and form them into a matrix, and then you calculate the determinant, if the determinant is 0, then that goes with dependent. And if the determinant is not 0, then that goes with independent. Okay, so that's how to go through and test whether vectors are linearly independent or not. All right, and then finally, we're going to look at eigenvalues and eigenvectors. All right, so eigenvalues and eigenvectors, this comes out of an interesting problem, and that problem is when does a matrix times a vector equal a constant times a vector? All right, so here on the left-hand side, we have, this is a matrix multiplied by a vector. And on this side, we have a scalar multiplied by a vector. And the question is, when do we end up getting the same value? Now, so first of all, you might be questioning, wait, is that even possible? Is it even possible that a matrix times a vector could equal a scalar times a vector? Well, the answer is yes, right? So we know from the previous stuff that we've done that AX, if you multiply that together, you could get B, where B would be a vector. If X is a vector, an n by 1 thing, then we would get n by 1 here. And we know that if you took a scalar multiple of a vector, then that would still be a vector, right? So if you took 1 times a vector, or 2 times a vector, or 7 times a vector, then that would still be a vector. And so it's definitely possible. Yes, it's possible. So then the question is, when does this happen? All right, well, what we can do is we can start off by assuming that we can do it. All right, so if you take AX, we're going to assume that AX does equal lambda times X. And then if that's the case, we could take the lambda and move it over here. Okay, and then if that's the case, we could take this and we could throw in an identity matrix. Okay, so X times the identity is going to be X, so we can do that. And then if you notice, we've got 2 things that are multiplied by X. We could factor those out, and we would get A minus lambda I times X equals 0. So if this is true, right? If this is true, then this is true. Right? Because all I did was just move stuff around. These are equivalent. This is equivalent to this, which is equivalent to this, which is equivalent to that. All right, so if this is true, then this is true. All right, and so once we get to this point here, our question is, when is this going to be possible? When could we do this? Well, so the answer to that question is going to, so what it's going to do is what we're looking for is when we can do this when X is not 0, right? You could always put an x equals 0 here and do that. You could always take this times 0 and get this and get that to be 0. So what we want to know is when could we take this and multiply it by something other than 0 and get 0, right? So let's just write that out. When so a minus lambda I times x, where x is not 0, would we get 0? Okay, well, so the answer to that is where that's going to come from. Okay, this is going to seem that it's going to come out of nowhere, right? So if a minus lambda I were invertible, then what would happen? What if a minus lambda I were invertible? Right, if a minus lambda I were invertible, then what we could do is we could go through and take this and multiply by a minus lambda I inverse, a minus lambda I times x equals a minus lambda I times 0. All right, so if a minus lambda I were invertible, then we could go through and multiply by the inverse on both sides. And if we did that, a minus lambda I inverse times a minus lambda I, that would give us I times x. And then anything times 0 is 0. And so we would get x equals 0. If a minus lambda I is invertible, then we get x equals 0. But what we want is we want to know when this times x is going to be 0, where x is not 0. So we want to know when x is not 0, when is this going to be the case? And so because of that, what we're going to do is we're going to specifically look for when a minus lambda I is not invertible. So we're going to look for the opposite of this situation that we just went through here. So we want to know when is a minus lambda I not invertible. Right? Because if a minus lambda I is invertible, then that tells us that x is 0, and we want to know when this is true when x is not 0. Okay, so that's, I don't know if you can follow that, but that's the idea, is that we want to know when this is true and x is not 0. If this is true and a minus lambda I is invertible, then that forces x to be 0. And so what we're looking for is when this is not invertible. All right, well, when is a minus lambda I not invertible? That would be when we know, what do we know about the determinant? Our determinant test, if the determinant is not 0, then it's invertible. If the determinant is 0, then it's not invertible. So what we want to know is when is the determinant equal 0? Right, so what that's going to do is that's going to go through and it's going to tell us when we could go through and have this equal 0 where x is not 0. All right, so that's what we're going to end up looking for. All right, so let's just jump into an example. So I don't know if you can follow all that. That was a little bit more complicated. Didn't seem quite as complicated when I wrote it out on my notes, but anyway, so it's not that complicated when it comes to actually doing the problem. So let's go through and do a few of these and do one of these, and then you'll be able to see that it's not that complicated. All right, so we've got a is 3 minus 1, 4, negative 2. And the question is, or I guess not can, but when does a times x equals lambda times x? Okay, and then so that's another way of saying when does 3, negative 1, 4, negative 2 times x equal lambda times x. And then what we can do is we can take this and move it over. So this is when does 3, -1, 4, -2 times x minus times x equals 0. And that's another way of doing 3 minus lambda, -1, 4, -2 minus lambda times x equals 0. When is this true? That's the same thing as saying when is this true, which is the same thing as saying when is this true, which is the same thing as saying when is this true. And then all that gobbledygook on the previous pages, this is only going to be possible if the determinant of this is 0. If the determinant of this is not 0, then that means it's invertible, and that would force x to be 0. So we want to know when is the determinant of this equal 0. We want it to not be invertible. So you go through and do the determinant. What was it? 3 minus lambda. -1, 4, -2 minus lambda. And we want it to equal 0. We want it to not be invertible. All right, and so the determinant of a 2x2 matrix, you take this times this minus this times this. So we're going to have 3 minus lambda times -2 minus lambda, and then minus 4 times -1, so minus -4. Okay, this times this minus this times this. All right, and then if you multiply this out, you're going to get -6. And what we got? We got +2 lambda minus 3 lambda. So that's going to be minus lambda plus lambda squared plus 4 equals 0. So we're going to get lambda squared minus 4 minus 2. Oops. Lambda squared minus lambda minus 2 equals 0. And so this is lambda minus 2 times lambda plus 1 equals 0. So we get lambda equals 2 or -1. So if lambda is 2 or -1, then that means that the determinant is 0, which means that this is not invertible. So we could go through and have solutions for this where x is not 0, which means that we could have solutions to this, which means that we could have solutions to this, which means that we could have solutions to this. And so all these things become possible when lambda is 2 or lambda is 1. These things are called the eigenvalues. They are the things that make it possible. Those are the possible circumstances under which we could go through and have this situation be true. Have this guy be true. Okay, so the question is, if you go back to the beginning here of this section, we said eigenvalues and eigenvectors. Well, what about this? So the eigenvectors are the x's that go, they're the non-zero x's that go with these eigenvalues. So to go through and find the x, so what we found is we found the lambda. We found the thing that you put here. We have the a, it's right there. We have the lambda now, but we don't know what the x is for when this would be true. All right, and so to go through and find that x, you need to go through and take the lambdas and plug them in. All right, so let's go ahead and do that. So you could take the 2, and if you plug it in, so what do you plug it into? You're going to plug it into this equation right here. So that's the one that we want. All right, just 1 second. So if lambda equals 2, then what happens? We're going to get, plug it in, you should get 1, -1, 4, -4, x1, x2 equals 0, 0. All right, so I took this equation right here, plugged in the lambda, and I did write out the vectors for x and for 0. So I plugged in the lambda value and I wrote out the x and 0. Okay, and so these are the steps that you're going to follow here. First, take this, and instead of writing it in terms of this matrix equation, they're going to translate it over to an augmented matrix. So we'll have 1, -1, 0, 4, -4, 0, ... And then to solve this, we could go through, we could take -4 times the first row and add to the second. 1, -1, 0. And if you do that, you're going to get 0, 0, 0. Okay. And then once you've gotten to that point, what we can do is we're going to translate it now into in terms of a system of equations, right? So we're going to use we're going to have x1 minus x2, right? So this is the coefficient of x1. Here's the coefficient of x2. And then the augmented here, that's where the equal sign goes, and then 0. And then since we don't have anything, for a 1 for this second row here, that's when we go through and use the free variable. You get x2 equals x2. And then from there, you could take this, and this is x1 equals x2, x2 equals x2. And so what we've got here is that x, which is x1 over x2, equals 1, 1 times x2. Okay, so this is the eigenvector. That tells you the value of x, or the multiples of x anyway, because there's more than one eigenvector, there's an infinite number of eigenvectors. It's all the multiples of 1, 1. And that's this x2 over here tells us that it's not just 1, 1, but it's all the multiples of that. So that tells us all the different eigenvectors that we could go ahead and plug in along with our eigenvalue, right? So our eigenvalue up here, we've got our eigenvalue, and then we've got the eigenvectors that went with it. And if you take the eigenvalue and the eigenvector and you plug them into this, it's going to make this true. So that's going to be when is a times x equals lambda times x. Well, when is that true? It's true when lambda equals 2 and when x equals 1, 1, or any multiple of 1, 1. And you could go ahead and you could test that yourself, right? So we could go ahead and pop this in. So we've got, let's go ahead and test it. So we've got a is 3, -1, 4, -2. Right, so that's our a. Did I copy that right? 3, -1. Yep, that's right. Okay, and we said, so that's our a. And our question is, if we take that and we multiply it by our x, and what did we say our x was? Our x was all multiples of 1, 1. So you could just pop in 1, 1 there, or a multiple of it if you wanted. There's x. And then the question is, does that equal, that should, is that going to equal lambda times x? Well, so lambda, what did we say lambda was in this case? Lambda is 2. Does that equal 2 times 1, 1? All right, and we can go ahead and check that. So let's take x and multiply it by this. So you take 1, 1 and multiply by 3, -1. So we're going to get 3 minus 1, 1, 1 times 4, -2. You get 4 minus 2. All right, and that's going to be a 2 by 1 vector. And then we've got over here 2 times 1. That gives us 2, 2, just a scalar multiple of 1, 1. And here 3 minus 1 is 2, and 4 minus 2 is 2. So you get 2, 2 equals 2, 2. So yeah, so that's a scenario under which ax is going to equal lambda times x. And when is the matrix times x going to equal a scalar times x? That's going to be true when the scalar is 2 and when the vector is 1, 1. All right, and now let's go through just to practice. Let's go through and find the other eigenvector. So if lambda equals -1, yeah, -1. If lambda is -1, then this vector here, if lambda equals -1, what we're doing is we're going all the way back to here and we're plugging -1 into this. So if we plug -1 in, what's going to happen? So we're going to have 3 minus -1. So we're going to have 4 -1. Then we're going to have 4 and then -2 minus -1. That's going to be -1. So we're going to have 4 -1 and 4 -1. And then that's times x1, x2, 0, 0. And then you could go ahead and form the augmented version of this. And then, so these are obviously the two rows are identical. So that means you could take, you could take the top one and take -1 times it and add to the bottom one, and that would give you an all 0 row. And then from there, you could go through and turn this into a 1. We've got 1, -1/4, 0. And then we could translate this back. This is x1 minus 1/4 x2 equals 0. We've got a row missing, so the free variable x2 equals x2. And then you could do x1 equals 1/4 x2, x2 equals x2. So that means we get x equals x1 over x2, which equals 1/4 1 times x2. All right, and then there's one more little trick we can do here, which is we can multiply this by, since x2 could be anything, what we could do is we could multiply by 4 and turn this into 1/4, and then you could maybe use a different letter for that point, since we've taken x2 times 4. So it's still going to be all multiples of 1/4. Sorry, 1/4 instead of all multiples, but it looks a little janky if you use x2 in both of these spots, since you took 4 times 10. Basically, you took x2 is basically 4 times t, and so we went through and basically did a substitution to clean up the vector and make it look nicer. Okay, and so this is the eigenvector for the eigenvalue of -1. And similarly, you could go through and test this by taking these two things, where this is x, this is lambda, take x and lambda, pop them in, right? So if you put the x here, so what did we say it was? It was, you put 1/4. If you put 1/4 here and you put 1/4 here, and then you replace this 2 with a -1, then it will also end up being true. So that's going to be our other scenario under which we take a matrix times a vector and we end up getting a scalar times a vector. Okay, and so that's how to go through and find eigenvalues and eigenvectors. All right, so the content of this video is intended to be a review. So this is a quick overview of these subjects. So if you're interested in more depth, then you can go through and look for videos whose focus is the content of this video. So if you go to YouTube and search for eigenvalue, eigenvector, you can see a more thorough explanation of eigenvalues and eigenvectors and more examples of how to find eigenvalues and eigenvectors. If you're interested in more detail on linear independence, you can go to YouTube and you can search for linear independence, and you can find videos that are more focused on that subject. But anyway, this video is just intended to kind of be a quick overview, a quick review, because this subject, this content of this video is taught in a linear algebra class. This is a differential equations class. Okay, so this is just a quick overview for differential equations. Okay, so that's it. Thank you for watching, and I'll see you next time.